In this module, we will learn about excited states. We will also learn about internal and external conversion, fluorescence, intersystem crossing, phosphorescence, kinetics and rate constants, and the Stern-Volmer equation. Firstly, excited states, we will learn about them and how they are dissipated by internal and external conversion. Then emission of photon as fluorescence, intersystem crossing and observation of phosphorescence, the various processes involved and the rate constants, and finally we will learn about the quenching of fluorescence and the Stern-Volmer equation. It is observed that a colored solution continuously absorbs light to go to an excited state. If the excited molecules were not returning to the ground state, a stage would come when the molecule would stop absorbing radiation, as all the molecules would have gone to the excited state. The re-emission of energy by an excited molecule is discussed in this module, because this is what must be happening, because some of the excited state molecules must be coming back to the ground state to get re-excited, and this is what we will learn about in this module. The various processes will be discussed and in terms of a diagram called the Jablonski diagram. The Jablonski diagram depicts the various processes whereby an excited state returns to the ground state, and it is shown in figure, which shows the electronic and vibrational energy levels for some of the ground and excited states. The ground state is labeled as S0 because most of the molecules are found in singlet ground states, and that is why it is called S0, and all the upper singlet states are called S1, S2, etc. in order of increasing energy. The first excited singlet is thus labeled S1 and is the most important excited state, since all other excited states are extremely short lived and immediately drop to this state. Excitation usually takes a molecule to a high vibrational level according to the Frank-Condon principle, which you have already seen, that the molecule goes to a very high vibrational level because Frank-Condon transitions are all vertical. In less than 10 raised to the power of minus 12 second, the molecule relaxes to the ground vibrational level of the excited singlet state. This process is called vibrational relaxation or VR. Now, the excited state may get deactivated by any of two processes. One is internal conversion and the second is external conversion. These processes are radiationless and are thus represented as wavy arrows. In the Jablonski diagram, when a process does not involve radiation, you use a wavy arrow, and if it involves radiation, you use a straight arrow. When the deactivation is by collision with another molecule or a solvent molecule or the walls of the container, it is called external conversion, and if it is between the same kind of molecules, then it is internal conversion. In some cases, there may be a crossing of the potential energy curve of the upper state with the ground state, and the molecule may cross over to a high vibrational level of the ground state and then come to the ground vibrational level of the ground state by vibrational relaxation. This process is called internal conversion. So, in this process, there may be a crossing of the excited state singlet with the ground state, and at the point of crossing, the molecule crosses over to the ground state to a very high vibrational level, and from there goes to the ground state by losing energy as heat, and this is called internal conversion. There is no radiation either of these processes. If none of these competing radiationless processes occur, the molecule returns to the ground state by emitting radiation, and this is called fluorescence. It is the reverse of excitation, but it occurs at longer wavelengths due to the Frank-Condon principle. On excitation, the molecule is taken to a high excited vibration level of the excited state governed by the Frank-Condon principle. As you will remember, the excited state usually has weaker bonding, so a vertical transition takes it to a high vibrational level according to the Frank-Condon principle. After this, vibrational relaxation occurs, and it brings it down to the ground vibrational state from which fluorescence can occur. Since the energy difference is smaller for fluorescence than for excitation, the latter, that is fluorescence, occurs at longer wavelength, and this shift, this difference in the wavelengths is called the Stokes shift. And here in figure you can see what fluorescence is. On excitation, the molecule goes to a high vibration level of the excited state, then it loses energy by internal conversion, reaches the ground vibration level of the excited state, from which it emits radiation in the form of fluorescence, and this is at longer wavelength, and the shift is called Stokes shift. Only the 0-0 transitions for absorption and fluorescence coincide. Absorption shows the vibrational structure for the excited state, while in fluorescence the vibrational structure corresponds to the ground electronic state, because the molecule would be going to different vibration levels of the ground electronic state when fluorescence occurs, whereas when excitation occurs it is from V is equal to 0 level of the ground state to any one of the vibrational levels of the excited state. So, the spacing tells you something about the excited state vibrational spectra. There is still an approximate mirror image relationship between the absorption and fluorescence spectra. This mirror image relationship is observed for molecules that are rigid and such as polyaromatics like anthracene, for which other dissipative processes such as internal conversion do not occur. Fluorescence lifetimes are of the order of 10 raised to the power of -8 second. So, when other processes do not occur, that is internal conversion and external conversion, and this happens for flat rigid molecules which are like polyaromatics like anthracene, then fluorescence occurs, and fluorescence lifetimes, the excited state singlet has a lifetime of 10 raised to the power of -8 second. Sometimes there is a crossing of the potential energy curves of the excited singlet, which is called S1, and triplet T1 states. There is no T0 state because most molecules, in fact the majority of molecules have singlet ground states, which is called S0. T1 state is the excited triplet state, and in quantum mechanics you must have studied that triplet states are slightly lower than the singlet states. So, it is slightly lower in energy than S1, but the two potential energy curves may still cross. The molecule may cross over to the triplet state by a process called intersystem crossing, because it has gone from the singlet system to the triplet system. Once there, it cannot easily come to the ground state singlet, because this process, as you know, involves change in spin and is electric dipole forbidden. However, it returns to the ground state by a process which is called fluorescence. Since this is a forbidden process, phosphorescence is slow and typical lifetimes are larger than 10 raised to the power of -3 seconds. Unlike fluorescence, it persists even after the radiation is switched off, and it is enhanced by triplet sensitizers like molecular oxygen, which you know is one of the few molecules which has a triplet ground state, which transfers its triplet energy to the molecule. Since triplet states are lower in energy than excited singlets, phosphorescence occurs at a longer wavelength than fluorescence. So, here we have shown there is a crossing of potential energy curves. From the singlet manifold, the molecule moves to the triplet manifold to a higher vibration level, from which it comes to the V is equal to 0 level of the triplet state, and from there phosphorescence occurs to the ground state S0. Let us now understand the kinetics of the various processes involved, since they involve varying time scales, and kinetics is very important for this kind of dissipation of the excited states. So, we will discuss the kinetics of photochemistry. Photochemistry is defined as the study of processes initiated by light. Photo means light, and chemistry that happens after this is called photochemistry. The primary step in photochemistry is absorption of radiation, and we say that the intensity is equal to I naught, which is the initial intensity by the ground state S0. The only process that deactivates the excited state is fluorescence. The following two processes occur. The first one is S0 plus h nu of absorption, and with an intensity IA it goes to S1, and then S1 undergoes fluorescence with an intensity IF, giving you S0 back plus h nu, the frequency of fluorescence nu f. The rate of disappearance of the excited state S1 molecules is given by, as usual in kinetics, dS1 by dt is equal to IA, because this is the process whereby it is formed, and minus Kf into S1, where Kf is the fluorescence rate constant and is first order, and we can say IF is equal to Kf into S1. It depends upon the rate constant for fluorescence into the population of the S1 state or the concentration of the S1 state. The lifetime of the excited state is tau 0, and this is given by 1 by kf. As you know, in first order the lifetime is equal to 1 by the rate constant. The rate constant has units of second inverse, and tau 0 will have units of second. This is also called the intrinsic or natural lifetime of the excited state. There are other processes which may also deactivate the excited state. These include intersystem crossing, as we have just learned. For this we will call the rate constant as KISC, or internal conversion, for which the rate constant is KIC. In the presence of these competing processes, the set of equations gets modified to, first one is S0 plus h nu A with an intensity of IA gives you S1, just like we learnt about just now. S1 then with an intensity IF emits radiation and goes back to S0 and emits radiation of frequency nu f. So, the energy is equal to h nu f, and then S1 undergoes inter-system crossing with the rate constant of KISC to go to T1, and from there with an intensity of given by IP for phosphorescence, it comes back to S0 plus h nu P, where nu P is the frequency for phosphorescence, and then finally S1 undergoes internal conversion to come to S0. So, as in kinetics we apply the steady state approximation for the excited state S1, because that is short lived. We know that it has a lifetime of around 10 raised to the power of -8 seconds. So, we find out ds1 by dt is equal to IA, the process by which it is formed, minus the process fluorescence by which it is getting dissipated, minus kf into S1 plus minus KISC, the intersystem crossing by which it is reducing its population, multiplied by S1. These are all first order rate constants, minus KIC into S1, and this should be equal to 0, and which implies that IA is equal to Kf plus KIC plus KISC, and this multiplied by S1. Now, efficiencies of photochemical processes are described by something called quantum yields, which are defined as phi is equal to rate of the process that you are studying, that is the rate of the specified process, divided by the rate of photon absorption. The quantum yield for fluorescence is defined as the fraction of molecules undergoing fluorescence, and is given by phi f is equal to rate of fluorescence divided by rate of all the processes, which means that Kf into S1 is the rate of fluorescence divided by Kf plus KISC plus KIC into S1, and that means that this is equal to Kf by Kf plus KISC plus KIC. If there are other processes, those rate constants will also be added in the denominator. Due to these competing processes, the observed lifetime is reduced to tau is equal to 1 by Kf plus KISC plus KIC plus all these. The denominator is a sum of first order rate constants, and hence the quenching process remains first order. Thus, we may write the equation as phi f, the quantum yield for fluorescence, is equal to Kf by summation of Ki, and this is equal to tau by tau naught, which was in the absence of all the processes the lifetime. Hence, since other energy wastage processes reduce the lifetime of the excited states, phi f is less than 1 and tau is less than tau naught. The lifetime tau is related to the intrinsic or natural lifetime by tau is equal to tau naught into phi f, and the quantum yield is always smaller than 1. Besides these processes, quenching of fluorescence may also occur due to external molecules, as we had just noted with the walls of the container, with other solvent molecules or any other molecules. For example, dissolved oxygen promotes intersystem crossing and increases phosphorescence. In the presence of a quencher, quencher is something that stops or reduces the amount of fluorescence or phosphorescence, an additional second process has to be taken into account, S1 plus Q, where Q is a quencher, and this gives you S0 plus Q. It brings back S1 to S0, and the quencher may remain unchanged or go to the excited state. And now the equation that we were learning about, phi f is equal to Kf by Kf plus KISC plus KIC plus Kq into Q. An additional term Kq into Q comes, where Q is the quenching rate constant and Q is the capital Q is the concentration of the quencher. If we designate the quantum yield in the absence of quencher as phi f naught, we may write phi f naught by phi f by doing some mathematical manipulation. We get is equal to 1 plus kq into q, concentration of the quencher, divided by kf plus kisc plus kic, and this is usually written as 1 plus capital Ksv into the concentration of the quencher. This is called the Stern-Bolmer equation, and Ksv, the capital Ksv that we have talked about, is the Stern-Bolmer constant, and from this equation you can see that it is equal to kq by kf plus kisc plus kic, and this is equal to kq into tau. Now, if phi f naught by phi f, the relative quantum yield, is plotted against the concentration of the quencher, from this equation you know a straight line should be obtained and its intercept should be equal to 1 and slope will be equal to Ksv, the Stern-Bolmer constant. The relative quantum yield can be replaced by the relative fluorescence intensity. Instead of that, you can use this also, and which is If naught by If, and this is easily measured by fluorimeters, spectrophlorimeters, etc. Also, since the lifetime is proportional to the quantum yield, the ratio tau naught by tau may be used instead. If tau, the fluorescence lifetime in the absence of quencher, is known, kq can be determined from the slope of the Stern-Bolmer plot. The lifetime can be easily measured by observing the first order rate of decay of the excited state. Since the fluorescence intensity is proportional to the excited state concentration, a plot of log, natural log of If versus time gives a straight line with slope minus k, where k is the combined rate constant of all the processes and is the reciprocal of the lifetime tau. Larger the value of kq, more efficient is the quencher. Thus, among the halide ions, the quenching efficiency increases as chloride is less than bromide is less than iodide. And in figure we have shown the Stern-Bolmer plot for the measured data on the quenching of fluorescence of riboflavin dissolved in 0.02 molar acetic acid by halide ions. For this, the value of Ksv obtained is 6.3 decimeter cube per mole for quenching by chloride ions. The literature value of tau is 5 nanosecond. This gives a value of 6.3 decimeter cube per mole into 5 into 10 raised power of minus 9 second is equal to 1.3 into 10 raised power of 9 decimeter cube per mole per second for kq. It is a second order rate constant, and you see that the slopes are different. Iodide has the largest slope. Finally, a summary of what we learnt in this module. Excited states lose their excess energy by various ways. Radiationless processes are internal and external conversion. If the molecule survives these processes, it may undergo fluorescence. If the excited state has a long lifetime, it may undergo intersystem crossing to a triplet state. From here, it may undergo phosphorescence. All these processes are first order processes. An external molecule may also quench fluorescence. Since this involves collision, it is a second order process. The quenching of fluorescence is given by the Stern-Bolmer equation.